Okay. Well, so also a wonderful good morning from my side. I have the pleasure now to give you, let's say, the perspectives on priority mixtures and drivers of toxicity we are developing in solutions. And well, let's say the starting point is the multitude of chemicals we could have in the environment. So there are estimates that we have about 10 to the power of 60 possible chemicals below 500 Daltons. So not all of them will exist, but that's what is possible. 10 to the power of 8 chemicals we have even registered already in the CUS systems. In the CUS system, 10 to the power of 5 chemicals are, let's say, in daily use. And if we have a look to environmental samples, we see that we have a multitude of chemicals there. So typically 10,000s of peaks we find there. And when we are doing monitoring, we're focusing on 45 priority pollutants. So that this looks like a bit of mismatch, let's say. Well, so what do we have? We don't have individual chemicals in the environment, but we always have complex mixtures. And thus, I think it's a reasonable conclusion that, well, an assessment and prioritization of risk based on individual chemicals alone is not appropriate. On the other hand, of course, if we are dealing with all these 10,000s of chemicals, it's a mess too. So the identification, quantification, assessment, and so on of each and every compound in these mixtures, that's just not feasible. So how can we deal with this complexity? And well, we are doing that with, let's say, 3 pillars, or better 3 triangles. So the first one is about priority mixtures, one of the key subjects today. And the basic idea behind that is just, is it possible to simplify these complex mixtures by considering them as a mixture not of 10,000s of chemicals, but of less mixtures? And can we prioritize these mixtures? Then, of course, we have to look what is the impact of these mixtures, and are we able to identify drivers of mixture toxicity? And these are exactly also the discussion points we have in this workshop. Oops. Well, I think when we are talking about priority mixtures, and that's the first thing I would like to do here, I think things get easier if we don't start with priority mixtures, but we do a 2-step approach. First of all, checking what are possible mixtures we can deal with, what are relevant mixtures, so can we group chemicals to such mixtures, and then do a prioritization according to, let's say, importance or whatever, and here, obviously, risk is an important issue. So I would like to start just with a little overview that was, well, in my mind, when I was thinking about grouping of chemicals. First of all, it's about effects, effect-related, so chemicals with the same modes of action, affecting the same organisms or biological quality elements, having similar effects, let's say, on ecosystem functions, on ecosystem structure, whatever, and even maybe from a more mechanistic point of view, do we have maybe mixtures that are non-additive, synergistic, whatever. And the second part, I think, which is also quite important, where we can look at, it's exposure-related. Of course, most of the chemicals we don't use as individual chemicals, but it's commercial mixtures. They are produced, and there are a lot of co-products and byproducts, so we could have production-related mixtures. Of course, we are often dealing with use-related mixtures, so we're talking about pharmaceuticals, we're talking about pesticides, whatever. What is quite important, and I would like to talk a bit more about that later on, are emission patterns, wastewater treatment plants, road runoff, agriculture, whatever. Of course, we have the contamination patterns on different scales, measured, modeled, and so on. Fate-related mixtures, that's also something that is quite common. Think about POPs, for example, so persistent chemicals or volatile chemicals, hydrophobic chemicals. That's also related maybe to a compartment-related approach. So what are the chemical, the groups we have in water, groundwater, sediment, soil, air, and so on. And since we are solutions-oriented, I think, also the abatement perspective could be interesting. So do we have chemicals with similar abatement strategies would work? No? You see some of them here. And maybe we also have chemicals where common legislation will work on. So all different perspectives, let's say. And then I think it's good to go to prioritization. And I think most of us agree that risk is at least one of the key drivers of this prioritization. But still, if we go for risk, I think we have, well, different perspectives there. Yeah, so first of all, of course, the scale. On which scale do we look? At a local scale, on the river basin scale, on a global scale, on a European scale? That's quite different, I think. The timing is important. So we have a look on short-term risks, on long-term risks, rare events, frequent events, and the biosystem. So is it always a full ecosystem that is endangered, or is it important species that are endangered? And I don't think it's always easy to answer. So sometimes I think a local risk on drinking water or on an important fish species or whatever could be at least as problematic as a global risk on biodiversity if it's a small global risk. So I think that is something we also have to balance. Yeah, and then the question of solutions-directed prioritization. Can we do something like that? So are abatement options possibly a fourth dimension in this, let's say, prioritization? And I just give you one example, and that is, well, there are some data from the UBA, from the Water Framework Directive monitoring, and, well, about the chemical status. And what you see here is the chemical status in Germany. Everything is red. Everything is red because of a mixture of, let's say, ubiquitous chemicals, mercury and others. Is that a very high priority because we have it everywhere, or is it a relatively low priority because we cannot do much about it? It's, I think, really a question. If we remove them, then, this is also a picture in the same report, then almost everything is blue. So, does that mean we have no risk anymore? I'm not so sure about it. But maybe, well, it's a question. Are these of higher priority than these mixtures? I don't know. And particularly, what would be if we would really define the chemical status on those chemicals and on those mixtures that are really relevant instead of the priority pollutants? Well, just very briefly, of course, it also makes a difference, or it should be considered that we have a high temporal variability, for example, for pesticides. Of course, it makes a difference whether you measure in November and you get a completely different mixture in November than in May, for example. And particularly at peak events, you get sometimes quite high quite high exposure. Weather conditions, whether you have dry weather or rain weather, you get completely different mixtures. So I think these are all things that need to be considered. Yeah, how to do that? How to do this assessment or prioritization of relevant mixtures? And I think there are two complementary types of approaches. One is a component-based approach. We all know, of course. Well, starting with individual chemicals, individual compounds, either with hazards or with effects, and doing some modeling, coming up with predicted mixture effects. So what is the problem behind that? Of course, all relevant chemicals should be known, otherwise we cannot do it. We need the effect data for these chemicals. We need to select a proper mixture toxicity model, concentration, addition, independent action, whatever. And there is obviously a difference also between having that as a hazard-based approach or having that as a, let's say, mixture effect-based approach, and what could be in between or what could link both is a kind of tiered approach. So risk-based mixture assessment is typically using single components regulatory values, EQS values, and so on, and calculates, let's say, hazard quotients from the concentrations we find outside, divided by these regulatory values, and we can sum that up, and if we are above 1 at the end, we have, let's say, a problem, we have a significant risk. The problem, of course, is that we are using different species here, we are using different endpoints here, we are using different conditions, and so on. So it's a rather conservative approach. On the other hand, we have real mixture experiments using the same species, the same endpoint, the same conditions, and that's what I showed you on the slide before already, can predict relatively precisely mixture effects. Well, and Both are linked in a way, of course, the same philosophy behind, and we can use them maybe in a kind of tiered approach, starting with mixture risk assessment and refining that with mixture experiments in order to enhance realism. But of course, we are also losing conservatism there. Well, this is the approach I showed you before. There's a second one, of course, and that is a fact-based or whole mixture approach. And what are we doing there? We are taking the mixture from the environment and, subject it directly to, let's say, toxicity testing, effect testing. And what we get out there are, relative enrichment factors in order to reach a specific effect level. We can calculate that together with trigger values, whatever, and finally can, let's say, prioritize and assess the mixtures we see. Well, and that is what I would like to show you just in some examples. So we start, let's say, with the first two approaches, so effect-related based on modes of action, and even a bit further based on affected organisms and biological quality elements. And that's particularly what our colleagues in tools are doing in sub-project tools. So starting with the mode of action compilation for all these different chemicals we are finding in the environment. Then, of course, we need detection tools in order to detect the effects of these chemicals in the environment and mixtures thereof. And we demonstrate that this is working in case studies, Rhine, Danube, and others. So that is the starting point. So Wiebke Busch, in this case, did a very nice study focusing on all the chemicals we found in the environment, 1,000 chemicals, and tried to identify the modes of action behind that. And you see already there are a lot of modes of action with some predominant ones, neuroactive chemicals, for example. There are photosynthesis inhibitors, there are some endocrine disruptors, and so on. And I think that this is already a quite nice basis, because for these chemicals, I think, or for these modes of actions, we finally need, the effect-based tools. Do we have these common modes of action for different chemicals also, let's say, in lists like the EU priority substance list? Yes, of course, we have that. And that's just what I would want to show you here. So we have here, let's say in green, all these photosynthesis inhibitors that can easily be measured together with the same assay. We have dioxin and dioxin-like compounds, which are already defined as a let's say, effect-based type of mixture. Then we have these acetylcholine esterase inhibitors. On the watch list, we have these endocrine disruptors, specifically the estrogenic chemicals. And for them, of course, this could be a starting point for, the effect-based tools. Well, effect-based tools, that means bioanalysis of effect-related mixtures, and their solutions is doing a lot of work. We are basically, presently, testing 52 different bioassays on 100 different chemicals we selected as, let's say, top European water contaminants, and we're doing that, along this line of AOP, let's say, starting from the chemicals, and then, we have transformation, we have receptors, we have key events, up to the organism effects, and we have bioassays in all these, different points of such an AOP. Well, if we apply that in the environment, like here for the Rhine case study, similar things we have from the Danube, then we see, we find some chemicals, in this case 405 chemicals with chemical analysis. We did 13 different endpoints with bioanalysis, and then come up with, let's say, graphs like that, where we have the effects, and we have the chemicals that explain these effects. And what you easily see is that in some cases, in this case it's photosystem 2 inhibition, we see that with chemicals we can measure, we can explain a lot of the effect at the end. In other cases, and that is oxidative stress, here for example, but I could put here also fish embryo toxicity, for example, there we see that with the chemicals we can measure, we explain only a very, very minor portion of the effect. So here, I think it's only bioanalytical detection that helps. So it's not one chemical or few chemicals that are doing the job. Well, if we are going for, let's say, prioritization, because that was also something we wanted to do, and we want to do that on the basis of effect-related mixtures, then that's again by Wiebke Busch. So what did she do? She, sorted the chemicals according to different modes of action and calculated some hazard quotients based on concentrations that are found in the environment. And what you see here is that some of these effects have relatively high. For some of these effects, we have relatively high some hazard quotients, and this could be, of course, a basis for prioritization of these, let's say, groups of chemicals, effect-based groups of chemicals. A next step, of course, is to identify the drivers of mixture toxicity, because we don't always want to deal with a whole mixture, but maybe we find individual chemicals that are, can represent that in a way. Yeah, and there are at least 3 approaches we are dealing with in solutions. The first one is a mass balance approach. I think you all know, and you already saw in that figure before. This case, it's, Novi Sad Danube, and what do you do again? So you measure the effect and try to find the chemicals that are causing these effects from the chemicals you can measure, and using, let's say, a concentration addition approach, and see, in this case, we can explain 100% of the androgenic effect by these chemicals. Most of them are, let's say, steroids here. But what you also see here, we have 3 different sites, and we do that for one, the most contaminated one. For the others, we don't explain anything, because with the chemical analysis, we are below the detection limit, so we cannot explain that. No? I guess it's the same chemicals, but we are not able to measure them. Well, here's the same for anti-androgenicity. Another approach we are dealing a lot with since let's say almost decades, also in my lab, that's effect-directed analysis. So starting with a complex mixture, doing biotesting, and then trying to break that mixture up by fractionation, biotesting, and finally identify fractions which are causing the effects, and then try to identify the chemicals behind that. You see, that's the same example again from Novi Sad, and that is nicely, let's say, confirming what we saw before. And this is a very much site-specific approach, of course. You can do that side by side, and it's quite nice, but it's difficult to put that on a larger scale. Oh. Well, another approach, more on the larger scale, is but that's not true. I'm sorry. I know when I started. So that's the virtual EDA approach, an approach that's more correlation-based and tries to find, let's say, chemicals that are correlated to effects we find in the environment, so more a statistical approach, and also for that we have quite nice examples that works, here for example for mutagenicity. Well, non-additive mixtures, again, a very interesting thing. We don't know so much about that, but we just recently had a quite nice example, and I think it's not an exception, but it's something that is occurring quite often with respect to mutagenicity, where we have different compound groups, carbolines, aromatic amines, and other compounds forming together a highly synergistic mixture, which is not predictable so far from what we find for individual chemicals. Well, then we jump to the exposure-related thing with only with emission patterns. The rest I skip because I don't have the time. What is the idea behind that? The idea behind that is that, well, the pattern we find finally in a river, for example, that's just, well, let's say all the input from the different sources, starting with industry, land use, plant protection, wastewater treatment plants, and so on. And all these mixtures together, they are forming the chemical and also the toxicological fingerprint at the end. So it would be nice to explain, let's say in a whole mixture approach, this big mixture as a combination of these individual mixtures. Let's suggest that just for wastewater treatment plants. I think Here we have a chance that the toxicological and chemical mixtures can be finally estimated, let's say, from relatively easy parameters like number of inhabitants, standard of living, treatment, dilution. And if we have, let's say, these data and typical drivers of risks and effects, we already can predict what should we have there and is there something extra? Because that's always the interesting thing. Are there extra site-specific toxicants? But we have to discriminate them from the rest. Well, we tried to test this hypothesis in the Danube case study, also in collaboration with Norman, for example. And that's also a point where modeling and monitoring are going really hand in hand, because from modeling we get all these information and we get nice, let's say, emission maps predicted based on all these parameters. Well, of course, we have to do that with similar approaches for other sources. And I think the nice thing about it is that it really can reduce complexity, and we can identify and also discriminate typical site and typical drivers and site-specific drivers, and that would also help the abatement, because as long as we are in the case of typical expected patterns, we have maybe ready-made abatement options, like upgrade of the wastewater treatment plant or whatever. And if we have site-specific phenomena, we can focus on that with tailor-made solutions. Well, I already talked about modeling, that modeling is an important issue, and that is also something we are intensively doing there in in solutions. I'm sorry. Here we have such a model train starting with substance properties, about models about emissions, transport and fate, and finally risk characterization. And the good thing about that is that, of course, this covers all the chemicals, all the substances that are produced, although even those we don't find in the environment or we are not looking for in the environment. Well, we can cover the full time domain, not just sampling days. We cover the full spatial domain, much more than we can cover with monitoring alone. And, well, the more information we get, the more understanding we have. It's a kind of rapid assessment, and, we get a nice idea about, let's say, uncertainty. And that is the last point, just to show you what is the outcome of such a model approach. And, that's what we have here. This, is let's say, a distribution of chemicals. We, from modeling based on REACH and based on generic models. We can do that also based on hydrology-based models. And that is the outcome. So such distributions of chemicals as a potential mixture. We can compare that, of course, with ecotoxicity data, which also form such a distribution. We can overlay both of them in order to find so which are the chemicals or which part of the chemical is really posing a risk. And the bigger the overlay, the bigger the risk. That's at least the idea behind. And there we quite often find, or we typically find something like that a small percentage of chemicals is contributing the major risk. In this case, the top 2% contributing 99% of the risk. That is based on this, in agreement, let's say, with the Pareto Principle. Well, just a last evaluation of this Pareto Principle. Does it always work? I think for these component-based approaches, it really works. It seems to work, so it has been observed in experiments and field data analysis quite often. It's really like that few chemicals should explain, the effects. But, of course, that differs from water body to water body. It's getting a bit more complicated if we are coming to the whole mixture approach, because, when we are dealing with specific effects, estrogen receptor binding, PS2 inhibition, whatever, then it still fits. So we still have few chemicals doing the job. I showed you before with the oxidative stress. I could show you with fish embryo toxicity, whatever. It's at least in obvious disagreement with the observations for these more less specific effects, because there we typically are not able to identify individual chemicals. We are not able to do, when we do a fractionation, to get it in individual fractions. So obviously here a lot of chemicals are working together. So, well, let's come to the conclusions. I think you saw we have an enormous complexity of contamination. We try to simplify that by mixtures, or by seeing them as a mixture of plus-minus defined mixtures and plus site-specific toxicants. And of course, these mixtures need to be prioritized, like the chemicals too. So this could lead to priority mixtures, and of course also to drivers of toxicity. However, still a lot of open questions we will deal with in this workshop. So how to group, how to assess, of course, these two approaches I explained to you, how to prioritize, and how to get the data we need in order to do that. So, thanks a lot. I hope it was not, no, I was good.